for giving me a chance to give the title of my talk is finite time invariant and n-equivalence graphs, and I would like to study some finite time invariant net rings and graphs in this talk. An embedding of some circles into the three spaces called rings, and in particular, if it has just one component, it is called knot. We study National rings by using some diagrams and their invariants, and for each natural rings diagram, we assign we assign polynomial with the indeterminate with A, B, C, and so on. So by using the three actions shown in this figure, we can get a linear combination of graphs and circles like this one. At the last step, we have a polynomial with the indeterminate A, B, K, R, U, delta, and tau. So and in that rings diagram has various kinds of projection, which does not seem same but maybe the same. Step property can be studied by using right-masked moves, and there are three kinds of moves called introduced by right-masked, and to get a linked invariant, we should solve equations like arising from the second and third right-masked moves. And from the second and third right-masked moves, we get 47 equations. Here is some examples of the equations. To solve the equation is very difficult, and so we do not see all of the solutions of the equation, but Kaufman, Lins, and Kings showed that there are some specific solutions of the system of equations, and here is a generalization of the solutions which were introduced by them. All of the solutions can be represented by using this formula. I would like to study some properties of the periodic rings and symmetrical rings by using the state model introduced by Kaufman. So we introduce some notation to introduce some cell. We denote the polynomial ring generated by the 9 indeterminate by R, and we denote the ideal generated by the 47 equations by R, and the ideal generated by this cell we denote it by J, and we also consider a similar ideal generated by this one and denote it by J to the N. For given ring, we denote its mirror image, which is obtained from the ring diagram R by changing all of the cosines, and we denote it by R to S star. Here is the theorem to determine whether given natural rings are periodic or not by using the measure. If R is a P to the R periodic ring, then we have such a congruent relation, saying that we keep the polynomial obtained by R by using the scalar relation, and that of R star is congruent measure J to the P to the R, measure P J to the P to the R. Actually, by using the solutions in this equation, we can verify many rings whether it is periodic or not by using this theorem. I'll try to skip the proof of this theorem. Here is another theorem to determine whether a given ring is a periodic or not by using some torus knots. The theorem may be proved by using some scaling module obtained by the scaling relations defining the state module. Here is the theorem to determine whether K and or n similar or not. The n similarity is an important concept in studying knots because if two knots are n similar, then it has the same value for any finite time invariant should be less than n. And so there are a big open problem whether every distinct pair of knots are n similar or not. The problem may be solved by using some scaling module, and we may determine whether two rings are n similar or not by using this module, this congruence relation. Next, I would like to talk about the finite time invariant arising from some graphics theory. And for example, Miller's invariant and so on. Miller's invariant is a ring invariant, which can be regarded as generalization of a ranking number, and it is shown that it is a finite type in some sense. And actually, it is defined only K component rings, and in particular, this one is called Miller's triple ranking number. It was introduced by using the fundamental group of complement of the knot space. It is a rather complicated diagram, and so I skipped the detailed definition of the Miller's invariant, and we introduced some graphs to study the Miller's invariant. For a given ring with the three components R1, L sub 2, and L sub 3, we consider it is a cyclically ordered, and we consider a hexagon with the three non-adjacent edges labeled like this one. And we consider that E sub y is attached in L sub 1 opposite orientation. We will see on example of this what this means. We regard y as a y graph, and we also consider some new knots obtained from the ring R, and by using the y graph, which is called y graph connected sum, or just the y sum. And for any two components, R sub I and R sub j, we may also apply the y sum, and it is actually a band connected sum, and we use the following notation, which says that L sub 1 to 3 denotes the ring L sub 1 union L sub 2 and L sub 3, and L sub ij will denote the band connected sum of L sub I and L sub j. Here is an example illustrating the band sum and y sum of the rings. If we have two trivial rings like this one, and that we connect these two components by using a band like this one without any twist, then we get a new knot like this one. K sub 1 and K sub 2 are trivial, but the resulting knot is not trivial. And this is it is also proved that for any band sum of non-trivial not also non-trivial. Here is a figure showing the y sum of rings by using band. The band y is shown this. So for any given rings with three components, by applying the y sum, we have just a knot with only one component. And here Poirier gave us some combinatorial presentation of the Miller's invariant. Actually, Miller's invariant is a complicated one to calculate by using just the definition. There are some methods to compute the Miller's triple linking number. Poirier's presentation will be the most simple presentation of the Miller's invariant. Poirier introduced the formula by using Gauss diagram. Gauss diagram means a diagram with the arrows like this one. For knots like this one, we have crossings at here, and at here. And for each crossing, we assign an arrow like this one, and we fix a point here, and we denote it at here, and we consider the signs of each crossing, and we assign the crossing for its arrows, and the direction of the arrows is determined by the overpass. When we goes over, then it becomes the starting point, and we goes under the crossing, then it becomes the ending point. And here is another Gauss diagram corresponding the ring like this one. This ring is called the Borromean ring, and when we remove just one component at here, then we have a trivial ring. And this ring is used to study Miller's triple linking number. The crossing at here corresponds to the arrow at here, and the crossing at here corresponds to the arrow at here. And in this way, for each link or match, we can correspond the diagram, which is called Gauss diagram, with the arrows with sign plus or minus. Poirier showed that for any based Gauss diagram of a ring, we can represent the Miller's triple linking number by using this formula. This formula says that we consider the Gauss, we compute the number of embeddings of the subgraphs out here. So if we have a subdiagram like this one, or this one, or this one, then we sum the number of this subdiagrams shown here. In this way, we can get some integer for each triple link. And here is the definition of direct move. Direct move is defined for links. In this diagram, we assume that the outside of the shown parts are identical, and direct move is just a local move, and this one. And it is proved that any notch can be unlinked, unknotted by using direct move, and any link which have the same linking matrix also can be related by using direct moves. That finite invariant were also introduced by Stanford by using the direct move. I would like to introduce some notations to introduce the finite invariant by using the direct move. And for given ring diagram, we consider disjoint disks in our index like this one, and as a y is assumed to contain one of the two angles, the direct move, and for any subset of this one, we denote this set the ring contained by applying the direct move in S of y, like this one. Then we may define some relationship on the set of rings by using the direct move. If there exists some diagram satisfying this condition, then what is Ln L prime are said to be delta sub n equivalent. For the case of notch, it can be proved that this relation is equivalence relation, but for the case of rings, it is not confirmed whether the relation is equivalence relation or not. In particular, if L prime is trivial, we say that it is delta sub n trivial. The G measure freely generated by the set of all rings is really denoted by this one. The sum measure generated by the linear combination of this form will be denoted in a C sub n. We introduced some finite time invariant based on the delta moves. If V is the ring invariant taking values in a suitable abelian group, then we can extend it linearly onto the space GR. And if M is of the space C sub n, then we say that V is that finite time invariant of degree or order less than n. It is quite difficult to whether a given knot is delta finite or not. It can be studied by using some graphical theory, and we will give some criterion whether to given rings delta equivalent or in this talk. Let me show that Miller's preferred linking number is delta finite time invariant but not finite time. Finite time invariant is another kind of finite invariant which is introduced by using another usual crossing chain G, which is a local movement. Stanford showed that any two notches have the same value for any delta finite time invariant of degree less than degree or order less than if and only if they are delta sub n equivalent. The set of notches does not form a group because there are no inverse for any non-trivial, but the space of notch modulo delta from J group under the connected sum. So next we have the following theorem which says that gives a relation between delta sub n equivalence and periodic rings. By using this theorem, we may verify whether a given link invariant is delta finite or not, and whether two tangles are delta n equivalent or not. So if delta T and S are delta n equivalent tangles and V is the integral delta finite time invariant of order less than fit to the R, then we have such a congruence relation. This congruence relation may be obtained by using the scalar relation of the delta finite time and some singular theory of natural rings. As corollary, we can get a criterion called periodicity of periodicity of rings by using the Miller's triple linking number as following. As the Miller's triple linking number is finite time invariant of degree 1. We have such a criterion by using the Miller's triple linking number. And next we give some relationship between the delta finite time invariant and a polynomial. Actually, it is considered that the delta finite time invariant is very similar to the space of polynomial functions, and so there are many known results between the similarity of polynomial and finite time invariant of rings. And here is an example of delta finite time invariant, delta finite time invariant, and polynomial. By using this theorem, we may verify almost all not invariant whether it is delta finite or not. So when that is that n trivial tangle and with that finite invariant of degree, and the rings obtained by from T to the I, each value have a polynomial growth in I of degree less than n over m. So by using this theorem, we may find the upper bound of the finite time invariant. And this is the end of my talk.